Welcome back. Part 2 here in our series on step-up transformers. This is an old input transformer that I found on an old reel-to-reel recording setup, and you know, the interesting part about it is there's no markings on this thing to tell us the what these wires mean. So we're going to go through the process this morning of figuring out what all these wires are and if this is a suitable step-up transformer or not. It may not be. We will find that out. So the first thing I'm noticing here is it's got some wires that come out of one side of it and some wires that come out of the other side of it. And there's a pretty good chance that one side is the primary and one side is the secondary, but that doesn't necessarily always hold true. Another thing I'm noticing, it might be hard to see here, but this one, the wire is broken. So even though you could connect to this part down here, all that's holding it at this point is the sheath. So I'm going to have to be very careful with this wire and kind of cut it off right here and strip just a little bit of it because there's not a lot left right there. Okay, as you can see now, I've got each of the wire ends kind of stripped here. I just used a little old kind of hand-controlled wire stripper here. You have to be very careful. But I'm not real happy about the length of this little wire here, so I think I'm going to fix that real quick by soldering a longer piece onto it and put some heat shrink. I just hate to mess with something that short and risk kind of breaking it off down there, because these wires are fairly old now. I imagine this transformer is 50 years old or so, and a little bit brittle. Okay, now as you can see, I've soldered a longer piece of wire here onto this, and I've some heat shrink around it. So now I've got something to work with here, and I'm not so worried about breaking that little thing off down there. And nothing was holding that on but the cloth sheathing. Okay, to start to dissect this thing, this is really all you need to start with. You need an ohm meter here, set on ohms. You need a piece of paper, and all I have drawn on here is a primary and a secondary. There could be multiple taps on the primary, there could be multiple taps on the secondary, there could be a shield here in the middle, all sorts of things I just don't know yet. But what we're going to do is we're going to start out, and typically I will pick one side or the other and I'll start with it. And one thing I've noticed interesting here is this wire looks like it was originally black, and this one looks like it was originally black, and this one looks like maybe it was originally an orange color or something along those lines. So you know, that could mean you know, one side, the other, and then a center tap, possibly. I don't know. But what you do is you start just kind of going through here and connecting and see what you get. Okay, so between this one and this one I got 10.9 ohms. And what I'll typically do is leave this one in place, and I'll walk around. Oh, 21.5, so that's a good sign. 10.5, right, or 10.9. I'll just write that down, 10.9, and then the other one had 21.5. There's a good chance here that this is a center tap then between these two. In other words, 21.5 ohms of DC resistance, and somewhere in the middle here would be about 10.5 ohms. But I'm going to keep going around, and if you'll notice, I get no connection on this one. Let's see here. No connection on this one, and no connection on this one. So, good thing is, this is likely the primary and center, two windings and their center tap. So if I go here, I get the 10.8 on this side. Ooh, that's good to know. 10.8. So I'm just going to keep walking around, make sure there's no connections now between this second wire with all the others. Nothing. And nothing. And then I'm going to do the last one here. And I just like to double check them. We already know that this should be 21.5. and I think this should be the 10.8, and then this one here, no connection, no connection, and no connection. So we can deduce then that we have a, and I don't know which side it is yet, whether it's the primary or the secondary in this case, but I'm just going to take a lucky guess here and put a center tap right there. And what I could say is from here to here is 21.5, and from here to here is 10.8 and 10.9, if you can see that. And you know, we can double check that. Outer to outer, 21.5 now at this point, and on this first one we've now got 10.9. So I'll tell you what I'm going to do. I'm going to label these things at this point. And I'm just using a shipping label here, 4x6, and I've cut some little strips here, and I'm going to just label them and then start tagging on these things. Okay, and as you can see now, I've now labeled this one A, this one B here in the middle, and this one C, and they correspond now with my A, B, and C here. So the good thing is, I know that those are on one side of the transformer because they didn't electrically connect with any of these on the other side. The good news is I can kind of be done with that side, and now I've just got to figure out what's going on over here on this other side. So there again, let's just connect to one end and connect here to the second one, and we've got absolutely nothing off of that. And then let's connect to this other wire here, and we've got absolutely nothing there. So this wire is not connected to either one of these. Well, let's see if these two wires here happen to be connected to each other. Ah, they are. Interesting. So if I was to deduce something from that, so first thing we know is we've got 2.869 kiloohms, 2.869 k ohms across these two wires. And let me just double check again that this wire here is in no way connected to either one of these two wires. And we've already deduced that none of these other wires were connected to any of these. So that tells me that what I've got here is two wires here that are my second set of windings here, and this one, since it's not connected to anything, I'll show you what I believe it is. Okay, so what I'm drawing here is a wire that goes inside of this transformer that ultimately, as you can see here, gets grounded, but it does not connect to either the primary or the secondary windings inside of this thing. And what it acts as is a Faraday cage, in other words, electrical interference shield, and keeps it out of this transformer. Alright, if you'll notice now, I've labeled one here for S for shield, and then I've labeled this other one D and E. And if you'll notice, what we've got here is A, B, C with 10.9 ohms, 10.8 ohms, and 21.5 ohms here in between these two. And then what we got on the output over here is 2.869 kiloohms. And then we've got a shield wire here in the middle. And the reason I label these things A, B, C, D, E like that is at some point we've got to figure out the phase relationship between the primary and the secondary. And oh yeah, by the way, at this point in time, I don't know if this is the primary or this is the secondary, but if you watched part one of this video, if you'll remember, there was a direct proportional relationship between the number of windings on one side and the number of windings on the other side, and the voltage on the first side and the voltage on the second side. In other words, If you have less windings on this side and more windings on this side, it would be a step up transformer because you would actually get more voltage out on this side than you put in on this side. And the fact that this thing is reading here at 21.5 ohms across this whole primary over here, and this is reading 28.69 kilo ohms. Because this is in the kilo ohms, this would tell me that there is a lot more windings on this side. Because keep in mind, at DC resistance, like we're measuring here, these windings are nothing more than a wire wound resistor. And the more windings you have, the more resistance you have. So it tells me that there's less windings on this side because there's less resistance, more windings on this side because there's more resistance. And so this would be a step up from this side to this side. Now, you can also kind of do some math really quick and say, hey, the turns ratio on this one to the turns ratio on this one would kind of imply the voltage as well. But we're gonna do that a little bit differently, and I'll show you how we're gonna do that here in 1 second. Okay, up next I made a little spreadsheet just using Excel, and I titled this first tab here SUT1, and this is where we're actually going to feed this thing on the input. So you can see here we're going to start out with A to C here, and we're going to feed it with 1 volt AC peak-to-peak signal. And then we're going to feed A to B here and measure that output, and then we're going to measure B to C, feed B to C. And all of these will be measuring the output here across, I guess I could put D to E, like that. Okay, so we'll be measuring the output across D to E. And then from that, the rest of this we're going to be able to calculate, and I'll show you how to do that. So let's go look at how we're actually going to measure this stuff. Alright, so for this test setup, you just need a couple pieces of simple bench equipment. First and foremost, these two little leads right here are connected to a B and C connector here that ultimately feed up via this this little B and C cable into my signal generator. So any signal generator that can produce a 1 volt AC peak-to-peak sine wave, and you would also like it to be able to create at least a 1 volt peak-to-peak square wave for the test we're going to be doing today. But I'm just feeding down here, and if you'll notice I'm feeding into A here, and I'm feeding into C here with these two leads. And then hooked across that, I've got an oscilloscope probe that's going into channel 1 of my oscilloscope here. And I've got the oscilloscope connected here and kind of the ground tab, or the negative if you want to look at it that way, connected to the other connection here, and the center tap here is just floating free at this point. Now on the output here, what I've done is I've came across D and E here with just a set of banana jack jumper wires here, and they are feeding over and they are connecting to a 4700 ohm resistor. If you remember, when we're doing step up units here for phono, the input stage of a moving magnet phono preamp that uses an RIA curve, the first thing it sees is a 4700 ohm resistor. So this is as real to life as you can get. And then connected across this 4700 ohm resistor here, I've got a oscilloscope probe. So what that does is it lets me measure both the input here with this probe and the output here with this probe. So I'm going to switch over now and let you watch the oscilloscope as we do this. Okay, we've got the oscilloscope on at this point on channel 1 and AC coupling, and we're going to turn on the function generator at this point in time. And if you'll notice, we're feeding out with about 0.16 volts peak to peak. So we need to adjust the input here of our function generator as close as we can get it to 1 volt. Alright, that's pretty darn close right there, sitting at 1 volt. And let's flip to channel 2 then. If you'll notice, they're both in phase with each other. So I could go down at this point and denote that with the positive on C and the positive output of my reading being on D at this point, that things are actually in phase with each other. So let's take off channel 1 now so we can measure channel 2. And if we notice, we're getting out 17.25 volts on the output. And I'm going to go input that into the spreadsheet really quick. And then what we're going to do here, we're going to move our input over now. Instead of being going A to C, we're going to move it going A to B at this point in time. And if you'll notice, let's go back to channel 1 here. If you'll notice, we're way down here. It's a different reflected impedance because you're feeding different set of taps on this transformer, so you have to readjust the input here. Always make sure to do this when you change input connections, is always to come back along. Alright, I'm going to leave it right there. And now we're going to flip over. You'll notice still in phase with each other. And then we can measure the output here. And we're getting 28.35 going from point A to point B. And then let's switch over and go A to C. I'm sorry, I said that wrong. We're going B to C at this point, but I always like to come back and check my input here. And if you'll notice, it's down a little bit. So let's turn that up till we get to for what we're doing. And let's flip over here onto the output now. And we're getting 29.05 on the output. Okay, from that point, we can go back to our spreadsheet. Okay, we've now come along and entered all these values in. A to C with 1 volt in was 17.25 volts out, 28.35 and 29.05, and all that aligns pretty well. If you remember, we had a slight imbalance even when we measured the DC resistance. One had 10.8 ohms and the other had 10.9 ohms, which tells you there's a slight bit more winding on one side than the other. In other words, that center tap is not identically right in the very B here. It's not exactly in the very middle of this transformer. It's off to one side just slightly, with a few more turns between B and C than there are A to B. Okay, up next, we got to calculate ourselves the turn and voltage ratio. Well, the beauty of using 1 volt in and then measuring the output is you don't have a lot of math to do right here. You can figure it out just by saying, hey, we fed 1 volt in, we got 17 volts out. The turns ratio as well as the voltage ratio is 17.25. So for every 1 winding going from A to C, there are 17.25 windings on the output here. For every 1 winding going A to B here, there are 28.35 windings on the output at E to D or D to E. And then from every winding here between B and C, there are 29.05. All right, let's go figure out how to figure up the rest of this, the dB gain and the cartridge loading. Okay, if you'll remember this website I showed you earlier, this mh-audio.nl, it's great calculators on there, and this is the one on how to calculate, let's see how they titled it here, calculating loading. And the good news is here, if you wanted to do the math, you could yourself. You need to divide 47 kiloohms, divide it by the turns ratio squared, and that'll give you the number you're wanting to do. Or we can use this simple calculator here. We're going to leave that at 47 kiloohms, and we're going to change this to 17.25. And we're going to do a calculate here, and we're going to get out 24.74 dB of gain, 24.74, and our cartridge loading on this one would be 158 ohms. And then we can do the same thing here with the 28.35. Hit enter or hit calculate. And then we can come back over here and say, okay, that would give us 29.05 dB, and we would only have a loading of 58.5 ohms. And then last but not least, let's enter in our 29.05. Calculate. Oops, wrong way. And let's bring this back up, and our dB gain we have here is 29.26, and we have 55.7 ohms here on the output. Okay, we're back over on the oscilloscope, and I thought I would show you something here. I've switched the polarity around on the oscilloscope probe on the output just to show you what it would have looked like if things were not in phase. In other words, that's the input and that's the output, and that is both of them. So if the input was going up and the output was coming down and vice versa, that would be an out of phase scenario. So it's really easy from that to kind of deduce, hey, I just need to flip things around, and then I can mark my dots, and I know when, you know, which lead when I'm feeding with positive and reading with positive on the output would be in phase with each other. So just wanted to show you that. Okay, now what I'm doing is I'm feeding this thing on the input with a 1 volt peak-to-peak square wave, and I'm reading the output now at this point. And if you'll notice here, we've got a slight bit of overshoot here on the transient upward, and we've got a slight bit here of slope to this transient. And so if you flip this out though and look at that, it's pretty darn flat. I mean, there's not a ton of ringing. There's a little bit of overshoot and then it self-corrects, but there's not a lot of ringing back and forth like we saw in some of the pictures. You know, if you scale that thing all the way out there across the full thing, it's pretty flat frequency response across the whole range. So I'm actually pretty happy with how this thing turned out. And we could potentially do some loading across this 4700 ohm and cut this little clip out right here on a little bit of ringing. We can play with that. Okay, for purposes of illustration, I've kind of blown this square wave up pretty big here. And I thought you'd get a kick out of this, to be honest. What I've done now is in parallel with that 4700 ohm resistor, I've added a kind of a precision potentiometer, and I thought what we would do is start turning it until we get rid of this little clip over here. In other words, we're adding some cartridge loading resistor here. And if you notice as I turn this thing, what's happening? You're right, the overall output is going down, down, down. Okay, somewhere along there we've now gotten rid of that little spike on the output there. But if you'll notice, I'm down to 8.96 volts on the output versus when I originally you know, put this thing in, we were getting up there around 13 volts. And so now I can cut off my function generator here, and I can turn on my ohm meter, and I can come down here and measure the resistance of this potentiometer that I just used. And that is a 30k ohm resistor that ultimately brings this thing down perfectly in line with having no kind of transient ringing whatsoever. Nice little signal. What are we paying for it? We're paying the price of gain at the end of the day. So there's a lot of debate out in kind of the audiophile industry around whether you use these loading resistors to kind of bring everything into a perfect little square wave and you take the gain loss, or whether you don't. And a lot of it really comes down to the matching of how much gain you really need for the cartridge you're trying to use. So there's a little bit of I would call art in matching your step-up transformer to the cartridge you're using, to maybe the loading resistor that you would use to get this thing sounding perfect. But the good news about this thing is, man, it's got a really nice flat response to it. And just in case you wanted to see what I did there, I just ran another using a set of just banana jumpers over to this is a Blue Alps potentiometer here. And then what I was showing you here was that after I measured this thing to where it was just the right output for turning down the ringing. I measured across it here with an ohm meter, and that's where I came up with the, as you can see here, the 30k ohm resistor that it would take to do that. So you could then go inside your step-up transformer, and across the outputs you could put a 30k ohm resistor on the inside of this thing before you feed your outputs, and you would know that you would be feeding out a nice little signal. The thing is, you need to now go back through all the steps we did earlier with that 30k ohm resistor in parallel with this to kind of get back to the gain figures, so you could basically fill the spreadsheet out again, if that makes sense, now with that 30k ohm in parallel, and it would help you understand better how much gain you would get out of each of the inputs on this thing without having to have that transient spike. Okay, I've disconnected everything from this transformer at this point, but as you can see, we've got everything kind of pinned out, and I've shown you how to do that. I've shown you how to put phase dots now to tell that when those things are in phase. And I sort of hid something from you in the beginning. I told you this was an unlabeled transformer. Well, it's not. It's a Triad 32B-8 transformer. And the reason I told you it was unmarked is because it kind of is. I could not find anywhere on the internet any specs on this transformer, no matter how hard I tried. The only thing I could find, which I could have used in this whole process if I had wanted to, but I didn't, and that is the schematic for the device that I took it out of. And if you'll notice right here, it shows it being fed in here on one side. They're actually grounding. So this is actually coming out of the reel-to-reel tape heads, coming over here into the primary of this thing. If you'll notice, they didn't even use the center tap on this thing. But one thing it did show you here is that it does have the shield that I mentioned to you, and it's grounded. And then they're feeding out the outputs on this thing, and it's feeding right over through a grid resistor into a 12AX7 into the preamp section here. So I could have unveiled that earlier, made dissecting the transformer maybe a little easier, but I wanted you to see what it was like to dissect something like this, because I find a lot of these. I'm out and about at Hamfest. Anytime I see a small sized transformer mounted on something, if the piece of gear is cheap enough, like $5 or so, I'm buying it just to bring home, pull this transformer out and test it, because you just never know when you're going to get a good step-up transformer out of that. And I've been lucky enough to gather two of these things over time. This one was interesting. It had both of the little tabs broken off of it, and I ended up having to kind of dissect the transformer on the inside enough that I could get some little bolts in here to actually kind of match up with some tabbed bolt downs. But you can see I got them both labeled now, and in our next part of this video we're actually going to build a step-up transformer using these. Okay, one last thing I wanted to show you before I wrap this video up that I failed to, and that is, I had mentioned earlier that a good SUT had minimal phase shift between the input and the output. So what I've done here is I kind of adjusted my volts per division until I get the inputs and the outputs kind of aligned with each other here. And if you'll notice, I'm at 0.1 volts on one of these, and I'm at 2 volts per increment on the other. But I want to try to get them as close to being on top of each other as I can. And then if you'll notice right here, if you kind of drew a center point on this top sine wave, if you'll notice, there is more surface area open over here on this side than there is on this side. If you'll notice, see how quickly it kind of closes together here, but on this side it comes all the way down here before it kind of closes. It's telling me that the output is shifted a little bit from the input, but this is not bad. This is actually pretty darn good. So when I say minimal phase shifting, if your sine waves are pretty much on top of each other like this, and you have no distortion whatsoever, you've got pretty good pretty good phase shift figures here. Nothing to worry about at all. Okay, I'm going back to a slide that I used in the first video talking about what makes a good SUT. And so let's try to determine now, based on that, whether this is actually a decent step-up transformer to use or not. So the first one says most good SUTs will have a 1 to 10, 1 to 20, or 1 to 30, somewhere in those range turn ratio. Some having multiple secondary taps for multiple options. And if we come over here and look, we've got a 17.25 and basically a 28.35. You wouldn't use all three of these, although I guess you could, but you probably have kind of a low gain and a high gain if you wanted to. So you'd either get 24 dB of gain or 29 dB gain coming out of this thing. And then they load the cartridge properly for that given cartridge spec. All right, that's the one place I see the downside in this overall thing. So if you look at the cartridge loading here, the very most this thing could actually do effectively is about 158 ohms. So you like to be 10 times the actual internal impedance of the cartridge, so you'd need a cartridge with a fairly low impedance. So in other words, this would be probably a pretty good SUT, just may not work great with every single cartridge out there. If you'll remember some of what we had here on this slide, this one's looking for a minimum of 100 ohms, so this SUT would probably work pretty well with this Denon 103. It's suggesting about 400 ohms, where this one will only load up to 158. So it may work fine, but it may not be the greatest for this HANA EL. And this Dynavector is looking for 1K ohm or greater. So probably not the greatest SUT for this. But having said all that, I've seen the math and science done. And then I've seen you plug something like this up to a cartridge and it sound absolutely phenomenal, even though the math says, hey, you're going to lose a little gain because of it. Well, sometimes maybe it's a high output cartridge here. If you notice this thing here, let's see, it's going to put out 2.5 millivolts. This one 0.3 millivolts. And this one, what is it going to be? 0.5 millivolts. So even with losing some gain on this one by dropping down below this, you may be fine. That's what I'm saying. I've seen scenarios where the math, and there's a little bit of art to this whole game. So, if I had to knock this thing, so one, I would probably give it on this one. The fact it doesn't have a 1 to 10, if I was scoring this, and it only has the 1 to 17 and 1 to 28, I'd probably give it a 7 out of 10 on this one. Here, because of that cartridge loading, I'd probably give it a 6 out of 10. Here, on this flat frequency response, though, wow, I would give this thing a higher, probably on up there at a 8 or 9 out of 10. Minimal ringing, flat response, absolutely great transformer. Utilizes an internal electrostatic shield. It does. I'd give it a good 10 out of 10 on that, or 9 out of 10. Minimal phase shift from input to output. This one looks really good, at least an 8 out of 10. And the beauty of this thing is it is an old Triad transformer. I'm telling you, these old Triad units, you look at the price tag of some of them on eBay and they're insane, similar to some of these Western Electric and the Altex, Fairchild's, others. So my guess is this thing has some pretty high permeability of the core material in these. So based on as many positives as this thing has, even though it's got maybe a few negatives here, I think this would be a great SUT, worth building. Would probably work great with some cartridges and maybe not so great with others. That's kind of the way this whole SUT game rolls. And but you've got at least got a high and low switch here to play with. You could also play with the loading resistors on the inside the SUT, loading in parallel with that 4700 ohms it's going to see on the next stage to cut down on a little bit of that ringing that we saw. So all in all, I'm going to give this one a big thumbs up, and we're going to move forward and build this thing and see how it actually turns out. Who knows? Thanks for watching, everybody. Stay tuned for part 3.